Look up at the night sky. What do you see? A scattering of stars, maybe a planet or two, the pale glow of the Milky Way. It all seems peaceful, almost familiar. But here's the unsettling truth. What we can see is less than 5% of the universe. The rest is a ghostly enigma, a cosmic hall of mirrors filled with forces and phenomena that defy everything we think we know. Take the Fermi Paradox, for example. With billions of galaxies, each home to countless stars and planets, the math says we should be swimming in alien civilizations. So where is everyone? The silence of the universe isn't just eerie, it's a screaming clue that reality is stranger than we've dared to imagine, and that's just the beginning. Dark matter, an invisible scaffold holding galaxies together, whispers through space without a single atom ever brushing against us. Black holes, those cosmic vacuum cleaners, don't just swallow light, they warp time itself, stretching seconds into centuries for anyone unlucky enough to drift too close. Even the vacuum of space isn't empty. It's a seething quantum foam where particles blink in and out of existence like static on an old TV. The universe isn't just weird, it's a carnival of the inexplicable, and every discovery peels back another layer of the surreal. That's why we're diving into 30 truths about the cosmos that'll make your jaw drop. From rogue planets hurtling through the void to the chilling possibility we're living in a simulation, these aren't sci-fi plot twists. They're real, peer-reviewed head-scratchers that'll make you question everything. So buckle up. By the time we're done, you'll see that glittering night sky for what it really is. The thinnest veneer over a reality far wilder, darker, and more magnificent than we ever dreamed. Here's something that'll bend your mind. The universe has a temperature, not just pockets of heat from stars or planets, but an actual baseline warmth that fills every inch of space. Imagine you're floating in the deepest void, far from any galaxy where it should be freezing. But instead of absolute zero, you'd feel a faint, uniform glow about 2.7 degrees above it. That's the cosmic microwave background radiation, the leftover heat from the Big Bang itself. It's the oldest light in existence, stretched and cooled over billions of years but still detectable, like the embers of a cosmic fire that never fully went out. What's wild is that this isn't some abstract concept. You're soaking in it right now. Those static snowflakes on an old analog TV, about 1% of that fuzz was actually this primordial radiation, whispering directly from the birth of the universe. Scientists detected it by accident in 1965, when two radio astronomers kept picking up a mysterious hum that came from every direction, no matter where they pointed their antenna. At first, they thought it was pigeon droppings messing with their equipment. Turns out they'd stumbled onto the echo of creation. And here's the kicker, this heat isn't just some relic. It's proof that space isn't truly empty. Even in the blackest void, there's energy, a sea of photons from a time when the cosmos was a seething plasma, so dense and hot that light couldn't travel more than an inch before bouncing off another particle. When the universe finally cooled enough to become transparent, that light burst free, and we're still catching its dying breath 14 billion years later. So next time you shiver on a cold night, remember space itself is keeping a faint but steady warmth, the universe's way of saying, I was here first. Think about the last time you stood on a beach, letting handfuls of sand slip through your fingers. It feels infinite, doesn't it? Scientists estimate Earth's beaches hold roughly 7 quintillion grains of sand. That's a 7 followed by 18 zeros. Now hold onto that number, because here's the cosmic punchline. There are more stars in the observable universe than all those grains combined. Our Milky Way alone is home to somewhere between 100 and 400 billion stars, and that's just one galaxy floating in a sea of at least 2 trillion others. Wrap your mind around that for a second. Every grain of sand you've ever seen wouldn't even make a dent in the star count of a single galactic neighborhood. What makes this even wilder is the Drake equation, the famous formula that tries to calculate how many alien civilizations might be out there. Even if only a tiny fraction of those stars have planets, and only a fraction of those planets are habitable, the numbers become staggering. Statistically, we should be drowning in cosmic neighbors, yet here we are shouting into what seems like an empty void. This paradox, the sheer abundance of stars versus the eerie silence, is one of astronomy's greatest mysteries. Are we alone? Unlikely. Are we missing something fundamental about the universe? Almost certainly, and here's the kicker, those 2 trillion galaxies we've spotted so far. They're just the ones we can see. The universe might actually be infinite, stretching far beyond our observational horizon. So next time you're at the beach, scoop up a handful of sand and remember, each grain could represent a star, and you're still holding less than a fraction of what's really out there. The cosmos doesn't just dwarf us, it humbles us, whispering that we've barely begun to count its treasures. Right now, as you gaze up at the moon, it looks placid, forever locked in its steady orbit around Earth. But here's a startling truth, it's slipping away from us. Thanks to precision laser measurements bouncing off reflectors left by Apollo astronauts, we know our lunar companion is retreating at nearly 4 centimeters every year. That might not sound like much, but over millions of years it adds up to something staggering. Rewind the clock far enough, and you'd find a moon so close it would dominate the sky, looming like a colossal pearl just 15,000 miles away, practically next door compared to today's 238,000-mile gap. This slow-motion escape is thanks to tidal forces, a cosmic tug-of-war between Earth and the moon. As the moon's gravity pulls on our oceans, it creates bulges of water that slightly lag behind Earth's rotation. This drag transfers energy to the moon, nudging it into a higher orbit like a parent gently pushing a child on a swing, each shove sending them a little farther out. But the effect isn't one-sided. Earth's rotation is also slowing down as it loses that energy. In the age of dinosaurs, a day lasted just 23 hours, and by the time the moon finishes its retreat billions of years from now, Earth's spin will have slowed enough that one side of our planet will permanently face the moon, locked in a gravitational embrace. Now imagine those ancient tides. With the moon so much closer, ocean surges wouldn't just be dramatic, they'd be apocalyptic. Waters could have towered hundreds of feet high, scouring coastlines and reshaping continents every few hours. Some scientists even speculate these monstrous tides might have played a role in early life's journey from sea to land, forcing creatures to adapt or perish. Yet for all its restless movement, the moon isn't abandoning us completely. Long before it drifts out of reach, the sun will swell into a red giant, likely engulfing both Earth and its fading companion. So while we still can, look up and appreciate that silver disk. It's been Earth's quiet dance partner for billions of years, and every second the space between us grows just a little wider. Hold up, your GPS knows Einstein was right. Every time you navigate using your phone, you're relying on satellites that account for time flowing faster in space than on Earth. That's not sci-fi, it's Einstein's theory of relativity in action. Clocks on GPS satellites tick about 38 microseconds ahead of ground clocks every day because they're farther from Earth's gravity, which warps time like a bowling ball on a trampoline. If engineers didn't adjust for this, your GPS would be off by nearly 6 miles within just 24 hours. The craziest part, this isn't a tiny error. It's proof that time itself is fluid, stretching and compressing based on speed and gravity. Now crank that up to cosmic extremes. Remember Interstellar's water planet, where 1 hour equaled 7 years back on the ship? That wasn't just movie magic, it's an exaggerated but scientifically plausible effect of orbiting a supermassive black hole. The stronger the gravity, the slower time crawls. Astronauts on the International Space Station experience a milder version of this after 6 months in orbit. They've aged about 0.005 seconds less than people on Earth. It's a fraction of a blink, but it means they've technically time traveled into the future. Here's the mind bender. If you could stand near a black hole's edge without being shredded, watching the outside universe would be like hitting fast forward. Galaxies would flare and die in moments, stars would streak like comets, and billions of years would blaze by in what felt like minutes. Meanwhile, anyone observing you would see your movements slow to a near freeze. Time isn't just a universal clock, it's a personal experience warped by where you stand and how fast you're moving. So next time your GPS recalculates, remember, it's not just guiding your drive, it's navigating the wrinkles of space-time itself. That moment you take a deep breath, you're inhaling the remnants of exploded stars. Every atom in your body, from the iron in your blood to the calcium in your bones, was forged in the heart of dying suns. When Carl Sagan said we are made of star stuff, he wasn't being poetic. It's literal astrophysics. After the Big Bang, the universe was nearly pure hydrogen with a sprinkle of helium. Everything heavier, the oxygen you breathe, the carbon in your DNA, was cooked up later inside stars, then blasted across space by supernova like cosmic shrapnel. Take the iron coursing through your veins right now. It started its journey in the core of a massive star where nuclear fusion smashed lighter elements together under crushing pressure. When that star ran out of fuel, it collapsed and detonated in a supernova so violent that it briefly outshone entire galaxies. That explosion hurled iron atoms across light years, where they eventually drifted into the cloud of gas and dust that formed our solar system. The same goes for gold in jewelry or the iodine in your thyroid. These elements are too heavy to form in ordinary stars. They only exist because of neutron star collisions, events so rare and energetic they're like winning the cosmic lottery trillions of times over. Here's what's even wilder. We're not just from the stars, we are them, temporarily rearranged. The average human body contains around 7 octillion atoms. That's a 7 followed by 27 zeros, and roughly 60% of them are hydrogen, the universe's oldest building block. The rest are heavier elements, each with a birth certificate signed by a dying star. That smartphone in your hand, its silicon and rare metals were once stardust. The water you drink, its oxygen was forged in a star's final convulsions before the sun even existed. So next time you feel insignificant under the night sky, remember, you're not just looking at the stars. You're looking at your extended family, the ancient furnaces that built you atom by atom. The universe didn't just create us, it recycled itself into us. And when our sun dies 5 billion years from now, its ashes might one day swirl into new planets, new life, another generation of stardust wondering where it all began. Picture floating near the center of our galaxy, where a massive cloud of gas and dust called Sagittarius B2 swirls in the darkness. If you could take a deep breath there, which you definitely shouldn't, you might catch a whiff of something bizarrely familiar: raspberries. That's right, astronomers discovered this interstellar cloud is packed with ethyl formate, the exact same molecule that gives raspberries their sweet, fruity scent. It's also one of the key ingredients in rum, which means Sagittarius B2 isn't just a cosmic bakery, it's a speakeasy. But before you imagine giant space raspberries or interstellar cocktail parties, let's break down why this matters. Molecular clouds like Sagittarius B2 are the universe's chemical factories where simple atoms collide and forge complex organic molecules. Ethyl formate isn't alone out there. Scientists have found everything from vinegar, acetic acid, to the building blocks of sugar, glycolaldehyde, lurking in these dusty nurseries. These aren't just random space spices, they're proof that the ingredients for life's recipe are scattered everywhere, waiting for the right conditions to mix. Here's the twist: Sagittarius B2 isn't actually smelling like raspberries. Space is a vacuum, so there's no air to carry scents. Instead, telescopes detect these molecules by reading their unique light signatures like cosmic barcodes. The raspberry connection, pure chemistry coincidence. but it's a delicious reminder that the universe loves recycling the same materials in wild new ways, whether it's a fruit on Earth or a gas cloud 25,000 light-years away. And who knows, maybe someday on a distant planet, some alien chef is baking with ethyl formate harvested from their own version of Sagittarius B2, blissfully unaware that across the galaxy, we're sniffing the same molecular whisper and thinking of summer berries. The universe doesn't just build worlds, it cooks up flavors. Imagine packing up for a road trip across Texas. You'd expect bustling cities, flickering streetlights, and endless highways. But instead, you drive for hours and find almost nothing, just a handful of tiny towns dotting a landscape so empty it defies logic. That's the Boötes Void, a cosmic desert so vast it makes our emptiest places feel crowded. Stretching 330 million light-years wide, about 0.2% of the observable universe, this region should host thousands of galaxies. Yet astronomers have only spotted 60. If the universe were a party, the Boötes Void would be the awkward empty corner where almost no one showed up. What's staggering is the scale of this nothingness. Picture our Milky Way as a single grain of sand. The average galaxy cluster would be a small handful scattered across a football field. But in the Boötes Void, you'd need to search hundreds of football fields just to find one lonely grain. Scientists call these voids the universe's large-scale structure, like the holes in a cosmic sponge. Most are smaller, but the Boötes Void is so unusually barren that some theorize it might be evidence of an even weirder phenomenon, a collision with another universe. Here's the twist: those 60 galaxies inside the void aren't just random stragglers. They're huddled together in a loose chain, like survivors clinging to a life raft. Some glow unusually blue, suggesting they've been cut off from galactic neighbors for so long they've evolved differently, their star formation frenzied and isolated. It's as if the void isn't just empty, it's hungry, having siphoned away galaxies over eons. Now zoom out further. The Boötes Void isn't unique, just extreme. Telescopes have mapped a web of similar voids, together forming a honeycomb pattern across the cosmos. Most galaxies cluster along the walls of these bubbles like dew clinging to a spiderweb. This structure hints at forces we barely understand, with dark energy likely pushing these voids apart faster than gravity can fill them in. So while the Boötes Void feels like a glitch in the universe, it might actually be a glimpse of the cosmic rulebook, one where emptiness shapes the universe as much as the stars do. On planets like Neptune and Uranus, a storm doesn't just bring rain, it brings diamonds. Yes, actual gemstones falling from the sky. These ice giants, with their crushing atmospheres and extreme pressures, turn methane, the same gas that powers your stove, into glittering diamond hailstorms deep beneath their clouds. Here's how it works. Methane, made of carbon and hydrogen, gets ripped apart by the intense pressure as it sinks toward the planet's cores. The carbon atoms, now free, are squeezed together so tightly they crystallize into diamonds, which then sink even farther, scraping through layers of slushy ice like cosmic buckshot. Scientists didn't just guess this, they recreated it in labs using high-powered lasers and plastic. Yep, polystyrene, the same stuff in disposable coffee cups, stood in for methane. When zapped with pressures similar to those inside Neptune, the plastic's carbon atoms bonded into microscopic diamonds in nanoseconds. It's a bizarre reminder that the universe loves turning the mundane into the extraordinary. What's even wilder, these diamond raindrops might not stay tiny. Some models suggest they could grow to millions of carats, forming thick layers around the planet's cores. Imagine an entire ocean of liquid diamond with iceberg-sized gems bobbing in it. And unlike Earth's diamonds, which take billions of years to form, this process happens continuously, a non-stop cycle of creation and destruction in the depths of these alien worlds. But here's the twist: Neptune and Uranus aren't the only places this happens. Exoplanets with similar conditions could have diamond rain too, meaning somewhere out there, a planet might be drowning in riches that would make every earthly jewel look like a pebble. Of course, mining them is impossible. These diamonds are born in crushing darkness, thousands of miles below toxic atmospheres. Still, it's a dazzling thought. The universe doesn't just make diamonds, it showers in them. Ask any child to draw the sun, and they'll reach straight for the yellow crayon. Even most adults picture our star as a golden orb, but here's the reality-bending truth. The sun isn't yellow at all. It's white, not off-white or creamy, but a piercing, almost blinding shade of pure white when viewed outside Earth's atmosphere. The only reason it looks yellow to us is because of the same atmospheric quirk that paints sunsets orange and makes the sky blue, a phenomenon called Rayleigh scattering. When sunlight enters Earth's atmosphere, shorter wavelengths, blues and violets, get scattered in all directions by air molecules. That scattered blue light is why the sky appears blue during the day. But what reaches our eyes directly from the sun is the leftover light, now skewed toward longer wavelengths, yellows, oranges, and reds. It's like nature's own Instagram filter, subtly altering the sun's true color before it hits our retinas. Space telescopes don't have this problem. Images from satellites like the Solar Dynamics Observatory reveal the sun as it really is, a searing white sphere with just the faintest hint of green at its peak emission wavelength. That green tinge is another surprise. Our sun's surface temperature around 5,500 degrees Celsius places it in the G2V spectral class, meaning its most intense light output is actually in the green part of the spectrum. So why don't we see a green sun? Because our eyes are terrible at judging color when something's too bright. The sun's light is so overwhelmingly intense that our brain blends all those wavelengths into what we perceive as white, with green drowned out by the flood of other colors. But here's where it gets wilder. The sun's color changes depending on how you measure it. Through a prism, sunlight splits into a full rainbow, proof it emits all visible wavelengths. From space, astronauts describe it as painfully white, like staring at a welding arc. And at high noon in Earth's thin upper atmosphere, pilots sometimes glimpse it as a cold, blue-white star, almost alien compared to the familiar yellow disk we know at ground level. This isn't just trivia, it reshapes how we understand stars. If aliens orbiting a planet with no atmosphere looked at our sun, they'd catalog it as a white star with greenish undertones, not the golden icon we've mythologized. Even crazier, our yellow bias might be uniquely Earth's. A sunset on Mars, where the atmosphere scatters red light instead of blue, makes the sun appear pale blue at midday and buttery pink at dusk. The cosmos has no fixed palette, only an endless interplay of physics and perception, proving once again that reality is stranger than the stories we tell about it. We think of space as an endless freeway where particles zip along at near light speed, but near the Milky Way's outer edges, something bizarre happens. Cosmic rays suddenly hit the brakes. These high-energy particles, born from supernova and black holes, should barrel straight through our galaxy's sparse frontier. Instead, they slow down as if slamming into an invisible speed bump, and scientists are scrambling to figure out why. One leading suspect, a colossal magnetic fence we can't see. Our galaxy is threaded with magnetic fields, faint but pervasive, like invisible spiderwebs. At the Milky Way's edge, these fields might ramp up in strength, creating a turbulent zone that deflects and decelerates incoming cosmic rays. Imagine a surfer riding a wave until it crashes into a hidden sandbar. The energy dissipates, the ride ends abruptly. That could be exactly what's happening to these particles, except the sandbar is made of magnetized chaos stretching tens of thousands of light years. But here's where it gets stranger. Dark matter might be the architect of this cosmic barrier. If dark matter, the mysterious substance making up 85% of our galaxy's mass, clumps near the edges, its gravitational pull could warp space in ways that act like a particle trap. Some theories even suggest dark matter particles themselves could collide with cosmic rays, sapping their energy like ghostly highway patrolmen handing out speeding tickets. The proof is in the data. Telescopes measuring cosmic rays detect a sharp drop-off in their energy levels near the Milky Way's periphery, as if something's filtering them. Even weirder, this barrier seems selective lower energy particles get stalled more than their high-energy counterparts, like a bouncer at a club turning away only certain guests. What does this mean for us? If confirmed, this invisible boundary reshapes how we understand our galaxy's ecosystem. It suggests the Milky Way isn't just a collection of stars drifting apart, it's a dynamic structure with defenses, a celestial fortress with walls we're only beginning to map. And if other galaxies have similar barriers, it could solve another puzzle: why the universe isn't flooded with even more cosmic rays. The cosmos doesn't just build galaxies, it gives them hidden armor. Einstein once called it spooky action at a distance, a phrase that perfectly captures the sheer weirdness of quantum entanglement. Picture two particles born from the same quantum event, like twins sharing an invisible bond. No matter how far apart they drift, whether across a lab or across the galaxy, change one particle's property, and its partner instantly mirrors that change. Not at the speed of light, instantly. This isn't theoretical. In 2017, Chinese scientists used their MISHA satellite to entangle photons and beam their quantum states down to ground stations 747 miles apart. The result: information effectively teleported between them, shattering previous distance records and proving entanglement works on planetary scales. Here's what makes this so mind-bending. Normally, nothing can outpace light, that's physics' ultimate speed limit. But entangled particles don't transmit information, they're more like two sides of the same cosmic coin. Flip one and the other flips simultaneously, as if space between them doesn't exist. Imagine throwing a pair of gloves into separate boxes and shipping them to opposite ends of the Earth. Open one box to find a left-handed glove, and you instantly know the other holds its right-handed match. No signal needed. Quantum gloves, though, don't decide which is left or right until you look, yet they always coordinate perfectly. China's quantum satellites exploit this by encoding data in photons, creating theoretically unhackable communications. Any eavesdropper trying to intercept the signal would break the entanglement, alerting both sender and receiver. It's like whispering secrets using a pair of magic dice that always roll matching numbers unless someone tampers with them. The real kicker: we still don't fully grasp how entanglement works. Some theories suggest particles access hidden dimensions. Others propose the universe is fundamentally interconnected at a level deeper than space-time. Whatever the answer, one thing's clear: the quantum realm doesn't play by our everyday rules. Those entangled particles aren't just defying distance, they're rewriting the textbook on reality itself. Think of everything you've ever touched, seen, or breathed: every star, planet, and speck of dust. All of it put together makes up just 5% of the universe. That's not a rounding error or a scientific estimate, it's a staggering admission of how little we actually know. The rest, a cosmic recipe of two invisible ingredients, dark matter and dark energy, making up 27 and 68% respectively. It's like walking into a theater, catching only 5% of a film's runtime, and having to piece together the entire plot from a handful of disjointed scenes. Dark matter is the universe's hidden scaffold, an invisible glue holding galaxies together. We know it exists because without its gravitational pull, galaxies would fly apart, their stars orbiting too fast to stay bound by visible matter alone. Picture a merry-go-round spinning so violently that children should be flung off, yet mysteriously staying glued to their seats. That's dark matter's handiwork, an unseen force anchoring the cosmos. But here's the twist: despite decades of hunting, we've never directly detected it. It doesn't emit, absorb, or reflect light, hence dark, yet its gravitational fingerprints are everywhere. Some theories suggest it's made of exotic particles that barely interact with normal matter, passing through you right now like ghosts through walls. Then there's dark energy, the universe's mysterious accelerator. In the late 90s, astronomers made a jaw-dropping discovery. The expansion of the universe isn't slowing down as expected, it's speeding up. Something is stretching space itself apart, and we've dubbed this unknown force dark energy. Imagine blowing up a balloon with tiny dots on its surface. As it inflates, the dots move apart. Now picture the balloon inflating faster and faster on its own, with no one blowing into it. That's the unsettling effect of dark energy, a repulsive force stronger than gravity on cosmic scales. What's humbling is how much we're missing. Normal matter, the stuff of planets, trees, and human bodies, is just the faintest ripple in a sea of darkness. Even dark matter, mysterious as it is, plays by some familiar rules, bending space-time with its gravity. But dark energy, it defies intuition entirely, behaving like an anti-gravity that challenges the very foundations of physics. Some theories suggest it's the energy of empty space itself, growing more potent as the universe expands. Others speculate it could be evidence of extra dimensions leaking into ours. Here's the kicker: if dark energy keeps accelerating the universe's expansion, distant galaxies will eventually vanish from view, their light stretched beyond detection. Future civilizations might gaze into the sky and see only blackness, with no clue that other galaxies ever existed. We're living in a unique sliver of cosmic time, late enough to understand the universe is mostly missing, but early enough to still see its fading fingerprints. The universe isn't just stranger than we imagined, it's stranger than we can imagine, with 95% of its story still untold. Black holes aren't just cosmic vacuum cleaners, they're celestial musicians. In 2003, astronomers made an astonishing discovery about the supermassive black hole at the heart of the Perseus galaxy cluster. It's been singing a single, impossibly deep note for billions of years, a B-flat 57 octaves below middle C, far deeper than any human could ever hear. NASA converted these pressure waves rippling through the cluster's hot gas into audible sound, revealing an eerie, pulsating hum that sounds less like music and more like the universe's deepest didgeridoo. Here's how this cosmic bass note works. As the black hole devours matter, it doesn't do so quietly. Tremendous outbursts of energy create pressure waves that propagate through the superheated plasma surrounding it, like dropping a stone into a pond but on an intergalactic scale. These waves travel at incredible speeds, compressing and rarefying the gas in regular cycles. The result, a sound wave with a period of 10 million years per oscillation. That's right, a single note lasts longer than human civilization has existed. The sheer scale of this phenomenon is hard to grasp. If you could stand next to this black hole, which you definitely couldn't, the sound would be a staggering 59 decibels, about as loud as a conversation on Earth, but vibrating your entire body with waves millions of light years wide. It's the deepest note ever detected in nature, so low that its wavelength measures 30,000 light years across. To put that in perspective, our entire solar system would be a mere speck riding these acoustic ripples. What's truly bizarre is why this happens at all. Most black holes are thought to be relatively quiet, but the Perseus cluster's central beast appears to be in a constant state of controlled eruption. The energy release isn't chaotic, it's rhythmic, creating these standing pressure waves that prevent the cluster's gas from cooling too quickly and forming new stars. In essence, the black hole regulates its entire galactic neighborhood through sound, like a drummer setting the tempo for an orchestra of galaxies. NAS, a sonification, the process of translating astronomical data into sound, lets us experience this cosmic vibration by speeding it up by 57 octaves. What emerges is a haunting, almost meditative pulse, proof that even in the vacuum of space where sound can't travel conventionally, the universe finds ways to sing. And here's the kicker: this might be happening everywhere, Recent observations suggest similar songs emanate from other clusters, hinting at a hidden symphony of black holes across the cosmos, each humming its own primordial tune. Hollywood got it dead wrong. Space isn't just some eerie void where explosions happen in perfect silence. The cosmos thrums with otherworldly noise, and we've got the recordings to prove it. NASA Voyager and Cassini probes captured something astonishing. The electromagnetic vibrations of planets translated into haunting soundscapes. Take Jupiter's magnetosphere, where charged particles spiral along magnetic field lines, producing eerie Whistler waves that ripple through space like cosmic radio static. These aren't sound waves in the traditional sense. Space's vacuum can't carry them, but when scientists convert the electromagnetic pulses into audio frequencies, the results are spine-tingling. One of the freakiest examples comes from Earth itself. Lightning strikes here generate electromagnetic pulses that travel up into the magnetosphere, where they bounce between hemispheres like a celestial ping-pong game. Converted to sound, these Whistler waves descend in pitch like ghostly slide whistles, a phenomenon first discovered in World War I when soldiers heard them through radio headphones. Today, we know these waves aren't just curiosities. They shape space weather, influencing how charged particles rain down on our atmosphere. But Jupiter's symphony puts Earth to shame. When the Juno spacecraft dove through the gas giant's polar regions, its instruments picked up something downright alien, a cacophony of pops, crackles, and shrieks as solar wind particles collided with Jupiter's monstrous magnetic field. The most unsettling, Jovian chorus waves, which sound uncannily like a flock of robotic birds chirping in the void. Scientists think these noises come from electrons surfing magnetic waves near Jupiter's poles, a natural particle accelerator operating on a planetary scale. Then there's Saturn's rings. Cassini's plasma wave instrument detected dust grains colliding in the rings, creating a hissing static that surges and fades like ocean waves. In the planet's auroras, ultra-low-frequency radio emissions pulse like a slow cosmic heartbeat, each thump revealing how solar wind energizes Saturn's magnetic field. Even the Sun belts out a roar. The Solar Dynamics Observatory captured magnetic loops vibrating like guitar strings after solar flares, their oscillations translated into deep, resonant tones. Here's the wild part. We're only hearing a fraction of the universe's soundscape. Plasma, the fourth state of matter, making up 99% of the visible universe, vibrates with electromagnetic songs we're just learning to decode. Black holes ring like bells when they collide, space-time itself vibrating with gravitational waves we can now detect. Pulsars spin with rhythmic radio pulses so precise they rival atomic clocks. The cosmos isn't silent, it's a vast, vibrating orchestra, playing a concert we're only beginning to tune into. So next time you watch a sci-fi movie where lasers zip by silently, remember, the real universe is anything but quiet. It's a roaring, whistling, singing expanse, and thanks to modern science, we've got front-row seats to the strangest show in existence. Look up at the night sky and you'll see one moon, but Earth's celestial dance is far more crowded than it appears. Our planet occasionally captures temporary companions, asteroids that hitch a gravitational ride around us for months or even years before vanishing back into the cosmos. These minimoons are the universe's way of reminding us that nothing in space is ever truly alone. Take 2006 RH-120, a car-sized asteroid that orbited Earth for 11 months starting in 2006. Unlike our permanent lunar neighbor, this visitor didn't come from the ancient collision that formed the Moon. It was just passing through when Earth's gravity pulled it into a wobbly, chaotic orbit. What's wild is how often this happens. Current models suggest Earth hosts at least one minimoon larger than 3 feet across at any given time, with dozens likely cycling in and out over centuries. Most are too small and faint to detect, but a few, like Kamaolwa, stand out. This curious rock, discovered in 2016, isn't just passing through, it's been orbiting alongside Earth for at least a century, trapped in a gravitational harmony that makes it more of a quasi-moon than a temporary guest. Here's where it gets even stranger. Kamolwa's composition suggests it might not be a random asteroid at all. Spectroscopy reveals its surface resembles lunar rocks, hinting it could be a piece of the moon itself, ejected by an ancient impact and later captured by Earth's gravity. Imagine that our planet might be trailed by fragments of its own cosmic sibling, a ghostly echo of the giant collision that shaped both worlds 4.5 billion years ago. These minimoons aren't just astronomical curiosities, they're golden opportunities for science. Unlike distant asteroids, they're practically in our backyard, making them prime targets for missions to study raw space rocks without the years-long journeys. NASA-planned Artemis missions could even attempt to retrieve samples from Kamolwa, offering a potential shortcut to understanding both near-Earth asteroids and the Moon's own violent history. But their ephemeral nature adds a layer of cosmic poetry. Most minimoons eventually break free, returning to their lives as main belt asteroids or drifting toward the Sun. 2006 RH-120, for instance, escaped Earth's pull in 2007 and now orbits the Sun like billions of others, a brief companion turned silent traveler. Yet their fleeting presence reshapes how we see our place in the solar system. Earth doesn't just have one moon, it has a rotating cast of temporary partners, each whispering that gravity's guest list is always changing. The moon isn't the silent, lifeless companion we imagine. It's a world that trembles under its own hidden stresses. When Apollo astronauts planted seismometers on the lunar surface between 1969 and 1972, they uncovered something startling. The moon experiences quakes just like Earth, but with eerie differences that rewrite our understanding of celestial mechanics. These lunar tremblers come in 4 distinct flavors, each revealing secrets about our satellite's inner workings. The most dramatic are deep moonquakes, originating 700 kilometers below the surface, far deeper than any earthquake could reach. These aren't caused by shifting tectonic plates, the moon lacks those, but by Earth's relentless gravitational tug. As our planet stretches and squeezes the moon during its orbit, tidal forces build up stress in the lunar interior until, crack, the brittle rock fractures like an overbaked cookie. The Apollo instruments recorded thousands of these events, some reaching magnitudes up to 5.5, strong enough to rattle dishes off a shelf if the moon had any. Then there are the shallow moonquakes, far more mysterious and violent. These originate just tens of kilometers down, last up to 10 minutes versus Earth's typical 30-second quakes, and pack enough punch to register as high as magnitude 5. Scientists suspect these might come from ancient faults formed when the moon's crust cooled and shrank billions of years ago, creating scarps that occasionally slip under stress. But unlike Earth's quakes that fade quickly, lunar tremors reverberate endlessly in the absence of water or atmosphere to dampen them. The real showstoppers are thermal moonquakes. Every lunar morning, as sunlight first kisses the frozen surface after 2 weeks of darkness, the crust expands rapidly, like a glass dish suddenly pulled from the freezer into an oven. This thermal shock triggers thousands of tiny quakes in sync with the sunrise terminator line's advance, a daily chorus of pops and creaks that would sound like a chorus of ice cubes cracking if anyone were there to hear them. Most bizarre of all, meteor impacts turn the moon into a cosmic drum. When space rocks slam into the surface at tens of thousands of miles per hour, they generate seismic waves that circle the entire moon multiple times before fading. Apollo seismometers caught one particularly violent impact in 1972, a 1-ton meteoroid that hit with the force of 11 tons of TNT, whose vibrations continued for over an hour. On Earth, such an event would fade in minutes, but the moon's dry, rigid structure lets seismic energy bounce like a ping-pong ball in a cathedral. These discoveries aren't just academic curiosities. Future lunar bases will need to withstand this constant shaking, especially the rare but powerful shallow quakes that could topple structures. And buried in the quake data might be clues to the moon's most guarded secret, whether it still harbors a partially molten core, sending faint tremors like a slow, distant heartbeat beneath the dust. Venus isn't just Earth's twin, it's the solar system's ultimate rebel, spinning in the opposite direction of nearly every other planet. While Earth and company rotate counter-clockwise like a graceful cosmic ballet, Venus does a full clockwise pirouette, taking a sluggish 243 Earth days to complete a single rotation. That means a day on Venus lasts longer than its year, since it orbits the Sun in just 225 days. This backward spin, called retrograde rotation, is one of the planet's greatest mysteries, and the leading theory involves a cataclysmic crash that rewrote its fate. Picture this: billions of years ago, a Mars-sized protoplanet slams into Venus at an oblique angle, hitting with such force that it flips the planet's rotation entirely. The impact might have been slow and grazing, like a cosmic sideswipe, but the gravitational tug of war could have literally reversed the planet's spin over millions of years. Alternatively, the collision could have knocked Venus onto its side, leaving it upside down with a technically prograde rotation that only appears backward from our perspective. Either way, the scars of this ancient violence might still linger beneath Venus's thick clouds, hidden from view but written into its very motion. Yet Venus's defiance doesn't stop there. While the planet itself creeps along at a glacial pace, its atmosphere races around the globe at hurricane speeds, a phenomenon called superrotation. Those sulfuric acid clouds, they complete a full lap of the planet every 4 Earth days, screaming eastward at 220 miles per hour. That's 60 times faster than Venus's surface rotates, creating a permanent maelstrom where winds howl unabated while the ground below barely budges. Scientists suspect this atmospheric sprint comes from a combination of solar heating and the planet's slow rotation. Sunlight blasting the cloud tops generates colossal temperature differences between day and night sides, driving violent circulation. With almost no surface friction to slow them down, Venus's topography is oddly smooth. These winds build momentum until they're practically unstoppable. It's like a pot of water boiling furiously while the stove beneath it barely flickers. Here's the kicker: Venus's backward spin and supersonic clouds might be linked. Some models suggest the retrograde rotation actually helps power the superrotation, creating a feedback loop where the atmosphere drags on the surface over eons, further slowing the planet's spin while the winds grow ever fiercer. It's a cosmic tug of war between rock and sky, where neither side wins, they just settle into an eternal, lopsided dance. So next time you hear Venus called Earth's sister planet, remember, this is the sibling that does everything backwards, cloaked in a tempest we're only beginning to unravel. From its possible violent origins to the storms that never sleep, Venus isn't just a world, it's a cautionary tale about how fragile planetary destinies can be. Somewhere in the cosmos, there's a planet that would make even the most extravagant jewel thief weep. PS RJ 1719-1438b. A world so dense and carbon-rich that scientists are confident much of it has crystallized into diamond. This isn't a metaphor or sci-fi fantasy. It's the brutal reality of stellar alchemy taken to the extreme. The story begins with a dying star, a white dwarf, the smoldering core left behind when a sun-like star exhausts its fuel. Most white dwarfs cool quietly into oblivion, but this one had a companion, a doomed planet or brown dwarf that strayed too close. Under the white dwarf's monstrous gravity, the companion was shredded, its material siphoned away until only the densest remnants survived. What remained was a corpse of pure carbon and oxygen, compressed under pressures so insane that carbon atoms were forced into a crystalline lattice diamond on a planetary scale. The result, a planet roughly 5 times Earth's mass but only half its diameter, orbiting its dead star every 2 hours in a blur of gravitational surrender. Here's what makes this diamond world even wilder. It's not alone. The universe seems to specialize in forging these carbon-rich planets around stellar remnants. Another candidate, 55 Cancri E, orbits so close to its star that scientists speculate its interior could be a vast ocean of liquid diamond, with solid diamond icebergs floating atop. The chemistry behind this is both simple and mind-bending. At extreme pressures millions of times greater than Earth's atmosphere, carbon atoms abandon their usual forms, locking into diamond's rigid structure simply because there's no room left for any other arrangement. But PSR J1719-1438b takes the prize for sheer audacity. Its host isn't just any dead star, it's a pulsar, a spinning neutron star that beams radiation like a cosmic lighthouse. Any atmosphere this diamond planet once had was likely vaporized long ago by those lethal pulses, leaving behind a bare, glittering core. The irony is poetic. A planet born from destruction, forged in conditions so violent they defy imagination, now floats silently in the void as the universe's ultimate trophy. And while mining it is impossible, it's thousands of light years away, bathed in deadly radiation. Its existence proves one thing: the cosmos doesn't just create diamonds. It builds entire worlds from them. What if everything you see, touch, and experience, every star, planet, and galaxy, is just a projection like a cosmic movie screen? That's the radical idea behind the holographic principle, a theory suggesting our three-dimensional universe might actually be encoded on a two-dimensional surface at its outer edge. Picture a hologram on your credit card, shine light on that flat sticker, and suddenly a 3D image pops out, now scaled up to the size of the cosmos. The mind-bending implication, the richness of reality, from the texture of a tree's bark to the spiral arms of the Milky Way, could be nothing more than shadows cast by information etched onto the universe's distant boundary. Scientists aren't just speculating about this, they're testing it. At Fermilab, physicists built the holometer, an experiment designed to hunt for the pixelation of spacetime itself. This ultra-sensitive device fires laser beams down two perpendicular 40-meter tunnels, measuring whether space wobbles at impossibly tiny scales. Why? If the universe is a hologram, there should be a fundamental limit to how smooth spacetime can be, like the graininess you'd see zooming in on a digital photo. The holometer sought those quantum ripples, the telltale static of reality being rendered from a lower dimensional code. Here's where it gets even stranger. The holographic principle emerged from studying black holes, those cosmic information shredders. When matter falls into a black hole, its entropy, a measure of information, appears to be proportional not to the volume it occupied, but to the surface area of the black hole's event horizon. This bizarre math suggests that all the data describing your existence right now could theoretically be compressed onto a flat sheet surrounding you. Think of it like the universe's ultimate zip file, where 3D is just an illusion our brains unpack in real time. The implications are staggering. If true, the holographic principle would mean that time, gravity, even consciousness itself might be secondary phenomena, byproducts of a deeper, flatter reality. It's as if we've spent centuries studying the images on a TV screen without realizing they're just pixels obeying the rules of circuitry behind the glass. Some versions of the theory even suggest the cosmic code could reside at our universe's birth moment, with the Big Bang acting like a projector beam casting the hologram we call home. For now, the holometer hasn't found definitive proof, but the search continues. Other experiments are probing spacetime's graininess using quantum-entangled particles or ultra-precise atomic clocks. Whether the universe is truly a hologram or not, one thing's certain: reality is far weirder than our senses suggest. The next time you gaze at the night sky, remember you might not be looking out into space, but at a screen with the true action happening somewhere beyond the edges of perception. Most stars will burn your hand to a crisp before you get within 1,000,000 miles, but not WISE 0855. This cosmic oddball, drifting alone just 7 light-years away, holds a record that shatters every assumption about stellar fire. Its surface hovers at a frosty -23 degrees Celsius, colder than a winter night in Siberia and downright touchable by cosmic standards. Meet the brown dwarf, nature's failed star that couldn't quite ignite. These celestial misfits form like stars, collapsing from vast clouds of gas, but they never gather enough mass to kickstart full nuclear fusion in their cores. Too big to be planets, too small to be true stars, they occupy a cosmic gray zone where the laws of stellar physics start to blur. WISE 0855 is the coldest known, so chilly that its atmosphere hosts something unimaginable on any other star: water clouds. Actual ice crystals floating in its upper layers, like a snowstorm suspended in perpetual twilight. Here's where the debate gets heated. Some astronomers argue brown dwarfs are just overachieving gas giants, pointing to worlds like Jupiter, which shares traits like swirling storms and banded atmospheres. Others insist the distinction lies in their birth. Brown dwarfs form alone from collapsing gas clouds, while planets coalesce in disks around stars. The truth might be messier. Recent discoveries reveal some brown dwarfs orbit stars like planets, while others drift freely like rogue stars, blurring the line between categories. The real magic is in the details. Unlike stars that blaze for billions of years, brown dwarfs are cosmic embers, glowing faintly with residual heat from their formation before cooling into planetary temperatures over trillions of years. Their atmospheres are laboratories of exotic chemistry, where iron reigns as liquid droplets and methane swirls in thick hazes. And because they emit mostly infrared light, they're virtually invisible to human eyes, ghosts in plain sight. WISE 0855 offers a glimpse of what happens when stellar ambition falls short. It's a reminder that the universe doesn't care for our neat classifications. It builds what it pleases, whether or not it fits the textbooks. So while we marvel at the brilliance of stars like our sun, spare a thought for these lukewarm loners, proof that even in failure, the cosmos creates wonders. The Milky Way isn't just drifting through space, it's racing towards something unseen at a staggering 14 million miles per hour, caught in the grip of a cosmic force so powerful it bends the paths of entire galaxy clusters. This invisible behemoth, known as the Great Attractor, lurks roughly 250 million light-years away in the direction of the Norma cluster, yanking thousands of galaxies toward it like a celestial riptide. But here's what makes this mystery truly maddening. We can't see it directly. Our view is blocked by the Milky Way's own galactic plane, a dusty, star-choked region astronomers call the zone of avoidance because it literally avoids letting us peer beyond it. This isn't just a case of bad cosmic real estate. The zone of avoidance acts like a thick curtain draped across our telescopes, absorbing visible light and radio waves from whatever lies behind it. Imagine trying to study a raging forest fire while standing in the middle of a smoke-filled room. That's the challenge scientists face when probing the Great Attractor's secrets. What little we've glimpsed through infrared and X-ray telescopes suggests an immense concentration of mass, perhaps a supercluster of galaxies weighing tens of thousands of times more than the Milky Way. Yet its exact nature remains one of astrophysics' most tantalizing puzzles. What's wild is how this gravitational titan reshapes our local universe. The Milky Way, Andromeda, and dozens of other galaxies in our local group are all part of a much larger parade called the Laniakea Supercluster, a filamentary web of galaxies flowing toward the Great Attractor like leaves caught in a slow-motion whirlpool. But here's the twist: the attractor itself isn't the end of the journey. Recent studies reveal an even larger structure, the Shapley Supercluster, lying beyond it, pulling the Great Attractor and everything else in our cosmic neighborhood toward itself. It's a gravitational matryoshka doll, with each layer revealing a bigger, more dominant force. The real enigma: the great attractor's pull is far stronger than the visible matter in its vicinity can explain. Just like dark energy and dark matter reshaped our understanding of the universe's composition, this anomaly hints at hidden mass distributions we've yet to map. Some theories suggest vast reservoirs of dark matter are clustered there, while others propose entire galaxies obscured by the zone of avoidance, their light swallowed before it can reach us. Efforts to pierce the veil are underway. Radio telescopes like Australia's Parkes and space-borne X-ray observatories are stitching together a patchwork image of what lies behind the Milky Way's dust. Each new dataset reveals more galaxies previously drowned out by our own galaxy's glare, slowly unmasking the architecture of this cosmic blind spot. One day, we might finally glimpse the true face of the Great Attractor, not just as a destination, but as a signpost pointing toward even grander structures lurking in the darkness. Until then, it remains a humbling reminder, even at 14 million miles per hour, the universe keeps its deepest secrets just out of reach. We think of space as an eternal vacuum, silent, empty, and unchanging. But step outside Earth's protective embrace, and you'll find a tempest raging, a maelstrom of invisible forces that make our worst hurricanes look like a breeze. The universe isn't just vast, it's volatile, with weather patterns so extreme they'd rewrite our textbooks if they happened here. At the heart of this cosmic storm system is the Sun, a roiling ball of plasma that doesn't just shine, it explodes, hurling billion-ton bursts of charged particles in our direction like a celestial pitcher with a grudge. These solar storms come in two deadly flavors: coronal mass ejections, or CMEs, and solar flares. A CME is the Sun vomiting a chunk of its own atmosphere into space, a cloud of protons and electrons racing outward at millions of miles per hour. A solar flare, meanwhile, is a burst of X-rays and gamma rays so intense it can outshine the entire Sun for minutes at a stretch. Together, they create space weather, a term that sounds almost cozy until you realize it includes radiation bursts strong enough to fry satellites and knock out power grids. The worst recorded case, the Carrington event of 1859, when a solar storm so powerful it set telegraph stations on fire and let operators send messages with the power disconnected. Auroras lit up skies as far south as Cuba, glowing so brightly birds started chirping in the middle of the night, mistaking the eerie light for dawn. If that happened today, experts estimate it could plunge continents into blackouts for months, frying transformers that take years to replace. Your phone, your GPS, even your refrigerator, all rendered useless by a storm that began 93 million miles away. Thankfully, Earth has a built-in force field, the heliosphere, a vast magnetic bubble blown by the solar wind that deflects most cosmic radiation like an umbrella in a downpour. But it's not perfect. High-energy cosmic rays, atomic nuclei accelerated to near light speed by distant supernova, still pierce through, bombarding astronauts and even altering cloud formation on Earth. Some studies suggest these rays might influence our climate, linking the cosmos to weather in ways we're only beginning to grasp. The real danger lies in the gaps. During solar minimum, when the Sun's activity wanes, the heliosphere weakens, letting in more galactic radiation. It's like Earth's magnetic shield developing temporary holes, and we've barely begun to map the consequences. Meanwhile, missions like NASA's Parker Solar Probe are diving into the Sun's corona, trying to predict these storms before they strike. Because in space, there's no weather forecast, just the silent buildup of forces that can erase centuries of human progress in a single starry night. Neutron stars aren't just cosmic oddities, they're nature's most perfectly polished marbles, sculpted by gravity so intense it flattens mountains into mere atoms. These stellar corpses, born from supernova so violent they squeeze a sun's worth of mass into a city-sized ball, boast surfaces smoother than any mirror we could ever craft. How smooth? Picture running your hand across a neutron star's crust. Any bump taller than a millimeter would be crushed flat in seconds by gravitational forces 100 billion times stronger than Earth. That's like taking Mount Everest and sanding it down to the height of a bacteria, all under the weight of a neutron star's relentless pull. To grasp why this happens, consider what neutron stars are made of. A single sugar cube's worth of their material would weigh as much as Mount Everest's 600 million tons packed into a space smaller than your fingertip. This isn't ordinary matter, it's atomic nuclei stripped bare, with electrons hammered into protons to form a sea of neutrons so dense it defies physics as we know it. Under that kind of pressure, matter stops behaving like a solid and starts flowing like a liquid, smoothing itself into flawless curvature. Even the star's magnetic field, strong enough to rip apart molecules from light years away, can't warp this perfect sphere. But here's what's even wilder: neutron stars spin. Some rotate hundreds of times per second, their surfaces moving at nearly a quarter the speed of light. Yet despite that dizzying motion, their shape stays impeccably round, with any distortion from centrifugal forces immediately corrected by gravity's vise-like grip. It's like watching a figure skater pull into a lightning-fast spin, except instead of arms tucking in, the entire star becomes a flawless, humming top. This perfection isn't just cosmic vanity, it's a laboratory for testing the limits of physics. When neutron stars collide, the ripples in space-time they create, detectable as gravitational waves, carry fingerprints of their smoothness. Any tiny imperfection would distort those waves, giving scientists clues about how matter behaves under conditions we could never replicate on Earth. So while neutron stars might look like featureless beads from a distance, they're anything but simple. They're gravity's masterpieces, where even the faintest ripple holds secrets about the universe's most extreme forces. Next time you see a glass marble or a polished sphere, remember, out there in the dark, nature has crafted objects so precise they make our finest human craftsmanship look laughably crude. The cosmos doesn't just build, it perfects. The moon might look like a dry, dusty wasteland, but hidden in its darkest corners lies a treasure more valuable than gold to future explorers: water ice. Billions of tons of it lurking in permanently shadowed craters near the lunar poles, where temperatures plunge to minus 250 degrees Celsius colder than Pluto's surface. These aren't just faint traces. Radar and spectrometers aboard orbiters like NAS, a lunar reconnaissance orbiter, have mapped thick sheets of ice, some possibly as pure as the glaciers on Earth. And the craziest part, this ice didn't form there naturally. It was likely delivered by comets, cosmic snowballs that slammed into the moon over billions of years, leaving behind frozen reservoirs in the only places the sun never touches. These shadowed craters are like nature's deep freezers, with walls so high and angles so steep that sunlight hasn't reached their floors in billions of years. Shackleton Crater, one of the most famous, is a 3-mile-deep pit at the moon's south pole where ice might lie just beneath a thin layer of dust. India's Chandrayaan-1 probe confirmed its presence by detecting the chemical fingerprint of water molecules absorbing infrared light, proof that even in the airless void, water found a way to survive. But how? When a comet hits the moon, its ice vaporizes on impact, but in these frigid, sunless pits, the vapor resettles as frost, slowly building up over eons like a celestial snowbank. The implications for human exploration are staggering. Water isn't just for drinking, it's a resource that can be split into hydrogen and oxygen, the key components of rocket fuel. A lunar base near these ice deposits could essentially mine its own propellant, turning the moon into a cosmic gas station for missions to Mars and beyond. Imagine a refinery at Shackleton Crater processing ice into fuel, cutting the cost of deep space travel by billions. Every gallon of water extracted on the moon is a gallon we don't have to haul from Earth's gravity well, where launching a single liter costs thousands of dollars. But the ice might hold secrets beyond practicality. Locked within those frozen molecules could be a record of the ancient solar system, clues about how water reached Earth in the first place. Comets are time capsules carrying pristine material from the solar system's birth. If lunar ice shares the same isotopic signature as Earth's oceans, it could mean our planet's water arrived via comet impacts early in its history. The moon's ice, untouched by weather or geology, might be the perfect archive to test that theory. Of course, mining this ice won't be easy. The same shadows that preserve it also create a labyrinth of darkness where solar power is useless and temperatures could shatter steel. Robots or astronauts working there would need nuclear heaters, headlamps piercing endless night, and drills capable of biting into rock-hard ice colder than dry ice. Yet the rewards outweigh the risks. Access to these frozen caches could make the difference between a fleeting lunar visit and a permanent human presence beyond Earth. So next time you look at the moon, remember, it's not just a barren rock. It's a desert with oases hidden in its coldest corners, waiting to quench the thirst of future explorers and propel humanity deeper into the cosmos. The water ice of the moon isn't just a scientific curiosity, it's the key to unlocking the solar system. What if reality isn't the ultimate foundation of existence but a simulation, an elaborate digital construct running on some advanced civilization's supercomputer? This isn't just a plot twist from The Matrix. Philosopher Nick Bostrom framed it as a trilemma. At least one of these statements must be true. 1. Almost all civilizations like ours go extinct before reaching technological maturity. 2. If they do survive, almost none care to run ancestor simulations, digital recreations of their past. Or 3. We're almost certainly living in a simulation right now. The argument hinges on probability. If future civilizations could run countless simulations of their ancestors, the odds that we're the original universe shrink to near zero. But how would we even test this? Some physicists suggest looking for glitches, tiny imperfections in the fabric of reality that might betray its coded nature. One signature could be pixelation at the Planck scale, the universe's smallest possible unit of space. Just as a digital image breaks into visible squares when zoomed too far, spacetime itself might reveal a granular structure if probed finely enough. Experiments like Fermilab's holometer have hunted for this quantum foam, firing lasers to detect minute spacetime jitters. So far, no dice, but the search continues. Another clue might lurk in the cosmic constants, the finely tuned numbers that make our universe habitable. The strength of gravity, the mass of an electron alter any by a fraction, and stars, planets, and life would never form. Simulation theorists argue this precision could reflect optimized code, like a programmer tweaking parameters to sustain virtual worlds, even more bizarre. Some propose that quantum indeterminacy, the way particles exist in superpositions until observed, might be a processing shortcut, rendering only what's necessary to maintain consistency, like a video game loading details as the player moves. Critics fire back with Occam's razor. Why invent a hyper-advanced simulator when a real universe suffices? Others point out that simulating consciousness, assuming it's even possible, would require unfathomable computational power. But the debate's real value lies in its audacity. Whether a simulation or not, the universe behaves as if it's governed by mathematical laws, and that alone is staggering. The possibility reshapes how we view existence, not as a given but as a question. If we're in a simulation, the programmers might be ancestors, aliens, or something beyond our comprehension. And if we're not, the universe is still mysterious enough to keep us wondering. Either way, the cosmos wins. Picture a planet untethered to any star, drifting through the eternal night of interstellar space. No sunrise, no seasons, just endless darkness stretching for light years in every direction. These are rogue planets, the cosmic nomads of our galaxy, and they might be the most common worlds in existence. Current estimates suggest there could be 20 rogue planets for every star in the Milky Way, meaning billions, possibly trillions, of these lonely wanderers are adrift in the void right now, invisible to traditional telescopes. Their origins are as violent as they are varied. Some were flung from their birth systems by gravitational slingshots during planetary billiards, while others formed directly from collapsing gas clouds, never knowing the warmth of a sun. But here's the twist: these frozen outcasts might not be lifeless wastelands. Deep beneath their icy crusts, tidal forces or residual geothermal heat could maintain vast subsurface oceans, hidden seas kept liquid by the decay of radioactive elements or the gravitational kneading of a massive moon. Take Jupiter's moon Europa as a blueprint. Its icy shell shields a global ocean twice the volume of Earth's seas, all heated by Jupiter's relentless pull. Now imagine a rogue planet with similar geology, its internal furnace churning for billions of years in the absence of starlight. Microbial life, if it arose before ejection, could persist in these pitch-black abysses, thriving around hydrothermal vents much like extremophiles do in Earth's deepest trenches. The odds get even stranger when you consider the sheer variety of rogue worlds. Some could be ice giants like Neptune, their atmospheres frozen into layers of exotic ices. Others might be super-Earths with thick hydrogen blankets, trapping enough geothermal warmth to maintain habitable conditions for eons. There's even speculation about steam worlds, rogue planets so rich in water that their subsurface pressures create hyper-dense ice phases unknown on Earth, with oceans sandwiched between layers of crystallized ice hotter than lava. Detecting these ghostly worlds is its own challenge. Without a star to illuminate them, they're nearly invisible but not quite. Astronomers hunt for them using microlensing, where a rogue planet's gravity briefly bends the light of a background star like a cosmic magnifying glass. Already, a handful have been spotted, including one roughly the size of Earth floating freely near the galactic bulge. Future telescopes like NASA's Roman Space Telescope could reveal thousands more, painting a clearer picture of this hidden galactic population. The most haunting possibility: some rogue planets might not be permanent exiles. Occasionally, one gets captured by a passing star, becoming an instant world in a new system. Imagine the spectacle: a frozen traveler, dormant for billions of years, suddenly warmed by a foreign sun, its icy shell cracking to reveal what the universe loves: its orphans. And among the countless rogue planets adrift today, at least a few might carry secrets even older than the stars. Light doesn't always race through the cosmos at a breakneck 300 million meters per second. Sometimes it stops dead in its tracks, and we've made it happen. In a lab at Harvard in 2001, physicists performed what seemed like magic. They brought light to a complete standstill inside a bizarre state of matter called a Bose-Einstein condensate. This isn't some optical illusion or trick of the light. They literally arrested photons mid-flight, freezing them in place like insects in amber, then released them unharmed moments later. The implications: they're rewriting how we think about information, memory, and even the future of computing. The key to this feat lies in the condensate itself, a supercooled cloud of rubidium atoms chilled to within a whisper of absolute zero. At these temperatures, atoms lose their individuality and merge into a single quantum wave, behaving less like particles and more like a unified superatom. When the team fired a laser pulse into this ultra-cold soup, they did something counterintuitive. They switched off a second control laser mid-flight. Without it, the rubidium cloud's optical properties changed dramatically, slowing the light pulse to a crawl before stopping it entirely. The photons didn't vanish. Their energy was transferred to the atoms, imprinting the light's quantum state onto the condensate like a fingerprint pressed into wet clay. Flip the control laser back on, and the atoms release that stored energy, resurrecting the light pulse with all its original properties intact. This isn't just a laboratory parlor trick. It's a gateway to quantum memory, where information encoded in light could be stored indefinitely in atomic vaults. Traditional computers rely on electrons shuttling through silicon, but quantum computers of the future might use trapped light to process data at unimaginable speeds. Imagine a communication network where messages aren't just sent but parked in transit, waiting for the perfect moment to continue their journey, or a computer that doesn't just calculate but remembers light itself, preserving quantum states too delicate for conventional storage. The Harvard team's frozen light lasted just milliseconds, but later experiments have pushed that to minutes, and the race is on to make it permanent. Researchers in Australia have even stopped light inside crystals at room temperature, sidestepping the need for complex cooling setups. The hurdles are immense: maintaining quantum coherence, minimizing noise, scaling up the technology. But the payoff could be revolutionary. Light-based memory might one day underpin unhackable quantum networks or exquisitely sensitive sensors capable of detecting gravitational waves from distant supernova. What's truly mind-bending is how this reshapes our understanding of light's nature. We think of photons as the universe's ultimate speedsters, yet here they are, brought to heel by human ingenuity. It's a humbling reminder that even the most fundamental constants of nature aren't immutable, just waiting for us to find the right lever. And tucked inside that ultra-cold rubidium cloud, there's a deeper lesson. Sometimes to move forward, you first have to know how to stop. If the universe is infinite and filled with endless stars, why isn't the night sky blindingly bright? This simple question, known as Fermi Paradox, haunted astronomers for centuries until it became one of the most compelling clues that the universe had a dramatic beginning. Picture this: every direction you look in space, your line of sight should eventually land on a star, stacking starlight upon starlight until the entire sky glows like the surface of the sun. Yet instead, we see darkness punctuated by pinpricks of light. The resolution to this paradox doesn't just explain the night's black canvas, it shatters the illusion of an eternal, unchanging cosmos. The key lies in two cosmic truths. First, the universe hasn't existed forever. Light takes time to travel, and because the Big Bang occurred roughly 13.8 billion years ago, we can only see stars within that observable horizon. Beyond that, light hasn't had enough time to reach us. It's like standing in a forest where the trees only stretch so far eventually. Your gaze reaches empty space because the trees beyond are too distant for their light to have traveled to your eyes. The second factor is redshift. As the universe expands, light from distant galaxies stretches into longer, redder wavelengths, sapping their energy until some fade into invisibility. Combine these effects, and the sky's darkness transforms from a riddle into proof evidence that the universe is not only finite in age but also dynamically expanding. Static universe models crumble under this logic. If space were infinite and eternal, every line of sight would indeed end at a star, no matter how faint. 19th century thinkers proposed dusty space or starless gaps as solutions, but these are band-aids. Dust would eventually heat up and glow just as brightly as the stars it obscures. The only lasting answer, a young, expanding cosmos where light's journey hasn't saturated every corner. Even the cosmic microwave background, the afterglow of the Big Bang, supports this, painting the sky not with starlight but with a near-uniform haze of ancient radiation. Here's the kicker: this darkness is temporary. In 1 trillion years, redshift will have stretched all but the closest galaxies beyond detection. Future civilizations might gaze up to a black sky with no hint of the Big Bang's fireworks, their night sky a far lonelier place than ours. We're living in a golden age of cosmic visibility, where the darkness above isn't just empty space, it's a time capsule, whispering that everything began with a flash. That gold ring on your finger or platinum necklace around your throat, they didn't just form in some mundane earthbound process. They're the shattered remains of dead stars that collided with cataclysmic force. While common elements like carbon and oxygen are forged in the fiery hearts of dying stars, the heaviest metals, gold, platinum, uranium, require something far more violent: the merger of two neutron stars, the universe's ultimate cosmic alchemists. Picture this: two city-sized stellar corpses, each so dense a teaspoon of their material weighs 1 billion tons, locked in a death spiral. As they collide, their incomprehensible gravity shreds both stars apart, launching jets of neutron-rich material into space at near light speed. In these fleeting moments, something extraordinary happens. Free neutrons bombard atomic nuclei with such intensity that they rapidly build heavier and heavier elements through what's called the R process, rapid neutron capture. The result, a cosmic fireworks show that manufactures gold by the Earth's worth in seconds, scattering these precious metals across interstellar space like celestial shrapnel. We've actually witnessed this process in action. In 2017, astronomers detected gravitational waves from neutron star merger GW 170,817. As observatories swiveled to look, they spotted something unprecedented, a kilonova, an explosion 1,000 times brighter than a typical nova, glowing fiercely with the telltale infrared signature of freshly minted heavy elements. Spectroscopic analysis confirmed the presence of gold and platinum in amounts that would dwarf our planet's entire supply. Based on the observed rates of these collisions, scientists estimate that a single merger event could seed an entire galaxy with enough gold to gild every planet 100 times over. Here's what makes this even wilder. We're not just talking about distant space gold. The atoms in your jewelry were almost certainly born in one of these collisions billions of years ago, adrift in a molecular cloud until our solar system formed. That means when you hold a gold necklace, you're holding stardust that survived a journey more harrowing than any fiction, first crushed into a neutron star, then vaporized in a collision, then flung across light years before finally condensing into a tiny piece of Earth. The platinum in your catalytic converter, that might be debris from a merger that happened before the sun even ignited. This cosmic origin story reshapes how we see the universe's resources. Every gold mine on Earth is essentially a neutron star graveyard, collecting elements so rare they can't form any other way. Even more astonishing, some of these heavy atoms might predate our galaxy, forged in mergers during the cosmic dark ages before the Milky Way took shape. The next time you admire a piece of jewelry, remember, its luster comes from a light show that outshone galaxies, its weight from a cataclysm that bent space-time itself. The universe didn't just make these elements, it detonated 2 dead stars to do it. The universe won't end with a bang or a whimper, it'll fade into an endless, frozen silence so profound it makes the void of space today seem lively. This is heat death, the grim finale predicted by the laws of thermodynamics, where every star burns out, every black hole evaporates, and even the fabric of matter itself unravels. But it's not the only possible ending. The cosmos might instead collapse in a fiery reverse of the Big Bang, a big crunch where galaxies, stars, and atoms are crushed back into a singularity. These two opposing destinies hinge on a cosmic tug-of-war between dark energy's relentless push and gravity's patient pull, and right now dark energy is winning. Heat death is the slowest, most desolate scenario. Imagine a universe where every proton, the building block of every atom, has decayed into radiation after 10 to the power of 34 years. Stars long gone, their ashes scattered into darkness, black holes evaporated via Hawking radiation, leaving only faint whispers of energy. Even the quantum foam of empty space would quiet to near absolute zero stillness, with temperatures so low that motion itself becomes impossible. The universe wouldn't just be empty, it would be tired, having exhausted every possible way to rearrange energy or matter. Time would lose meaning, stretching into an eternity where not even memory exists to mark what came before. But the Big Crunch offers a dramatic alternative. If dark energy weakens or reverses, gravity could eventually drag everything back together. Galaxies would merge, then stars, then atoms, heating the cosmos to trillions of degrees as it shrinks toward a single point. Space-time itself would warp and collapse, potentially triggering a new Big Bang, a cyclical universe where death breeds rebirth. Some theories even suggest the crunch might not be the end, but a reset, with each cycle tweaking the constants of physics slightly, producing a new universe with different rules each time. The wildest twist, black holes might outlive everything else. In a heat-death scenario, these gravitational monsters would be the last structures standing, slowly leaking energy over unimaginable eons until they too vanish. But some hypotheses propose that the singularity inside a black hole could birth a new universe with its own laws of physics, meaning our entire cosmos might be the offspring of a black hole from a prior reality. Whatever the true ending, the timescales are beyond human comprehension. The last stars won't flicker out for another 100 trillion years. Proton decay won't erase matter for 1,000,000 times longer than that. By then, if any intelligence survives, it'll face a cosmos unrecognizable to us, a relic of an era when light and heat still existed. The universe doesn't just die cold, it dies alone, with no witness left to mourn or remember. And yet, in that infinite stillness, there's a strange solace. Even the end isn't truly the end, just another turn in the wheel of cosmic possibility. From diamond rain on Neptune to black holes singing in cosmic B-flat, from rogue planets adrift in eternal night to the unsettling possibility we might all be living in a simulation, our journey through these 30 truths has revealed a universe far stranger than fiction. The cosmos doesn't just defy our expectations, it laughs at them, serving up phenomena that rewrite the rules of reality itself. Who could have imagined a planet made of solid diamond, or a void so vast it swallows galaxies whole, or that the gold in your jewelry was forged in the violent collision of two dead stars, scattering their priceless debris across the cosmos like celestial confetti? Yet for all we've uncovered, the most humbling truth is how much remains shrouded in mystery. Dark matter's invisible grip, dark energy's relentless push, these unseen forces make up 95% of the universe, and we've barely scratched their surface. Even the fabric of space and time might be an illusion, a holographic projection from some distant boundary we can't perceive. Every discovery peels back a layer, only to reveal deeper questions lurking beneath. But that's the thrill of it. The universe isn't a puzzle to be solved. It's an endless frontier, always ready to astonish us. Just a century ago, we didn't know galaxies existed beyond our own. Today, we're mapping the cosmic web and listening to the echoes of black holes. Who knows what tomorrow holds? Maybe we'll find life swimming in the hidden oceans of Europa, or crack the code of quantum entanglement to build unhackable networks. Perhaps we'll finally meet the neighbors or confirm we're alone in the silence. However the story unfolds, one thing's certain: curiosity is our compass. It's what drove us from cave fires to moon landings, from stargazing to simulating the birth of the universe. So keep looking up, keep questioning, and never stop marveling at the fact that we tiny, fleeting specks on a pale blue dot get to unravel these cosmic secrets at all. As Carl Sagan once said, somewhere something incredible is waiting to be known. And if this journey has shown us anything, it's that the universe never runs out of wonders. The next revelation could be just over the horizon, hidden in the spin of a neutron star or the whisper of a distant galaxy. All we have to do is keep searching.